Just complain about it a little more second semester.
Students just complain about it a little.
That sounds exactly like
Students do well considering their circumstances.
Oh, really? Are we gonna take
I'm not
up,
getting a notification.
Lily?
All right.
We're gonna take up
Surfaces in space. So we've already talked about one basic surface in space, a plane. So a plane is our first real surface in space. Our next surface in space is relatively familiar. A sphere. And we're going to say our sphere has center x0, y0, z0, and radius r. So based on what you know already about equations in the plane, what would you guess would be the equation of a sphere in space? Well, so we have our center is at x0, y0, z0. So what would you guess? Okay, I'll put that out here. Equals r squared. That's good. X squared plus y squared. That would be if our center was at the origin.
Which is always at the origin. It should never not be at the origin.
X minus x0.
Yeah, just say whatever the
Squared.
You didn't see the square?
It's cute. Actually, guys.
Squared. Plus, so this is a circle, right, in the plane, centered at x0, y0. There is going to be our standard equation of a sphere in space. So, and our sphere, the definition of a sphere is a set of all points x, y, z, with distance r from x0, y0, z0. So what this is the distance formula in 3 dimensions. We just add one piece for our z coordinate. And we mentioned before that our notions from 2-dimensional geometry still hold in 3-dimensional geometry. Distance formula, we just add a z component. Midpoint formula, we add a z component to find our midpoint. So for example, I don't want to go through the calculations, I just want to talk about this. So let's say we wanted to find the equation of a sphere with these points as endpoints of a diameter. So what would we do? How would we go about it? Find the midpoint. So the center is going to be at the midpoint between those 2 points. So the center is at the midpoint, and we remember how to find the midpoint of a segment, right?
No.
Average the x components, average the y components, average the z components. So 5 plus 0 divided by 2, negative 2 plus 4 divided by 2, 3 plus negative 3 divided by 2. So we find the midpoint, and then how do we find the radius? Yeah, find the distance between those 2 points and divide by 2. So the distance between the points is twice the radius. And then you'd have your radius, you'd have your center, and you could write your equation. All right, so now we have two basic kinds of surfaces. We have a plane and we have a sphere. Our third basic kind of surface is called a cylindrical surface. And a cylindrical surface, we're not talking, the normal cylinder that we're used to is an example of a cylindrical surface, but cylindrical surfaces are a larger group than just circular cylinders. All right, in space, our cylindrical surface will have an equation that only involves two of the three variables. And I guess to be completely accurate, we should say a nonlinear equation. Because if we have a linear equation with just two variables, we're talking about a plane. So we're going to have some kind of equation, not a linear equation, that involve only two of the three variables. The graph of the equation in a plane is called the generating curve. So what we need to do when we're thinking about surfaces now that we're basically we're not in the plane anymore, we're in space, we have to think about all three variables. So the mistake that most students make when we start working in three dimensions is they forget that we're actually in three dimensions. And these surfaces are not necessarily circular cylinders like we normally think of them. A circular cylinder would be a cylindrical surface with a circle as a generating curve.
So it's like a thing that's been pulled up.
Right, we take a circle in the plane and we pull it up along an axis. So mainly what we want to do now in chapter 11 is start working on visualizing these surfaces in space. In future chapters, we will use the surfaces for various things. But right now, we want to have an introduction and kind of a way to visualize it. So I want to look at a couple of cylindrical surfaces. So let's say we want to sketch z equals y squared. So we have a nonlinear equation with only two of the variables. So our generating curve is what kind of shape? This is a parabola. And this is going to be our generating curve. We can think of it being in the YZ plane. So if we want to sketch this, draw my coordinate system here. So here is z, y, and x. There would be the parabola z equals y squared, and I'm going to draw it over here as well in the YZ plane. There's our parabola, but x can take any value. So this parabola, this is z equals y squared on any plane that's parallel to the YZ plane. So the surface is going to extend out this way, like so. And it would extend back this way as well.
And this is talking only about a surface generated by this, not the solid area.
No, this is just the surface. So it would be kind of a parabolic shaped trough. And the trough is not a mathematical term, but that's,
Put that on the test.
if you put that on the test, that would be fine. But the technical name for this would be a parabolic cylinder. And we're talking about the surface, just this parabolic surface. So if I have part of a parabolic surface, this is for something else we'll do second semester, but I cut a paper towel roll in half, so that top part there is roughly that parabolic cylinder. Part of it, anyway. So, and I'm going to say x can take any value.
And is there a way that you can limit the range of the x values if you just added a...
Sure, you could say
Yes, you could make it
10 less than or equal to x less than or equal to negative 10 or something like that. And what we'll do during second semester is we'll talk about surfaces that are generated when this, or curves that are generated when this surface is intersected by another surface. All right, so there's one cylindrical surface. Let's look at another one. We want to sketch z equals sine x. So this is a nonlinear equation in just two variables. So our generating curve is a sine curve in the xz plane. So let's, there are my axes. And there's always at least one student that is extremely talented at drawing surfaces and can shade them and they look beautiful and perfect. That's not, my curves never look like that. So here's my generating curve. And this would be x equals pi. And here we'd come back at x equals 2 pi. And y can take any value. So we get a sine curve on any plane parallel to the xz plane. So we could stretch this surface over this way and we'd get, I'll do these in dotted lines. So we get something like this. And these are all connected.
So what would happen if they were not all the same? Is there a way you could do that? Make them not, so like you have guide curves that so you could mark a sine wave into something else if you did not have them?
It is possible. That's more advanced than we will talk about. So this looks like a corrugated roof. Sort of like a scroll, but it would continue. It would be infinite in this direction, infinite in that direction. So it's like a corrugated tin roof, or the layers between the layers of corrugated cardboard. So in general, a cylindrical surface, this is going to be more or less how you're going to sketch a cylindrical surface.
that what it's called? According to
I would just call it the technical name would be a sinusoidal.
sinular system.
We feel like extra credits.
Well, on many of them, I will ask you to on the next kinds of surfaces, I'll ask you to classify them. So there's some kind of more technical names, but we have come up with interesting names for various surfaces. One we came up with, there was a ham curve that we came up with.
What's a ham curve?
It's a curve when you rotated it looked like a ham, with the netting around it. So so we had the ham curve.
Last year we did volumes, we had the ham type.
All right, so that's our third kind of surface. We have a plane, we have spheres, plane spheres, cylindrical surfaces. Our fourth kind of surface is quadratic or quadratic. And these are the surfaces, cylindrical surfaces and quadratic surfaces are the ones that we end up using the most because they're typically easier to visualize, and we're more familiar with the techniques. For a quadratic surface, our book uses quadratic. It's more common. I think quadratic is a little more common. The equation will be a second degree equation. That involves all three variables. In some way. And we call the intersection of the surface with a plane the trace of the surface. And we're going to be interested in the traces in the coordinate planes. That's what's going to help us sketch these. The trace of quadratic surfaces are conic sections. So all of that stuff that we learned in pre-calc about ellipses and hyperbolas and parabolas, we use that a lot. Cones. So the trace of our quadratic surfaces are going to be conic sections of some kind. On page 812 through 813, they have a table of quadratic surfaces and their equations, what they look like. They give you some hints about the forms of the equations. You don't have to memorize the equations, but what we will do is we will work with them more and more and more and become more and more familiar with them. And after our lesson on Thursday, I have kind of an exploration that I found on a computer-based exploration. That reminds me, everybody make sure you have a computer. Or you can access a computer in class after our lesson on Thursday, because I have an exploration where you can manipulate the surfaces and you can drag some sliders and see some things that will help us visualize. So the table gives us our equations of quadratic surfaces. What I want to talk about is using the trace of a quadratic surface to help us visualize the quadratic surface. All right, so let's say we want to sketch and classify x minus y squared minus 4z squared equals 0. So this is a second degree equation that involves all three of the variables in some way. What I would do for this one, just because of its form, since the y's and z's are squared and x is not, I would write x equals y squared plus 4z squared. Either one of these is fine for the equation of the surface. And what we're going to do is look at the traces of this curve in the coordinate planes to help us sketch it. So in the xy plane, z equals 0, we get x equals y squared. So we can just think of z equals 0. So there's a parabola. The trace is a parabola in the xy plane. So where the surface intersects the xy plane, it creates a parabola. In the xz plane, that's where y equals 0. We get x equals 4z squared. Another parabola, but with just slightly different shape. And where for x equal a constant. So I'm going to say parallel to the YZ plane. Now, before I go on, why did I not say when x equals 0? What happens when x equals 0? Everything is 0, so you just have a point. So at the origin, it intersects the origin at a point. So parallel to the xz plane, where x equals a constant, we have y plus 4z squared, y squared plus 4z squared equals a constant. What is that? It's an ellipse, right? We would divide everything by the constant, and we'd have y squared over something plus z squared over something else equals 1. This is an ellipse. So on any plane parallel to the YZ plane, we get ellipses. And the ellipses are going to be larger or smaller depending on what our x value is. So let's make a sketch of this thing. All right. In the xy plane, we have a parabola. So there's a parabola in the xy plane. So that's flat in this plane. In the xz plane, we have a parabola. We also have a parabola, but it's just a little different shape. So that parabola is going to go, I'm going to go in blue. So that is in the xz plane. And I'll do this dotted underneath, like so. So this is below the xy plane. And then parallel to the yz plane, we get ellipses that connect these things. So I'll do those ellipses in green. So there's one ellipse that connects those parabolas. So what this shape is called, this is an elliptical paraboloid. And what the shape is, if we can visualize this, we have this parabolic shape that comes out of the screen, and it gets wider as we come out. So a small example of that would be the reflector of this flashlight. This would be a circular paraboloid. So the reflector is that shape of that thing coming out, and if this were wider, it will continue to be wider. But this was elliptical, so it's kind of squashed in one dimension. So this paraboloid. So the reflector of a flashlight is a circular paraboloid. If this were x minus y squared minus z squared equals 0, we'd have a circular paraboloid, because this equation would be y squared plus z squared equals a constant. All right. Questions there? Let's look at one more. And I want to talk about this one quickly because it's one that students continue to confuse for a long time. We want to sketch z equals x squared plus y squared. Sorry, z squared equals x squared plus y squared. So we're going to do the same thing. In the xz plane, we have z squared equals x squared, and we can simplify that to z equals, when we take the square root, plus or minus x. So what is that? Or what are those? Lines. In the yz plane, we get z squared equals y squared, or z equals plus or minus y, lines. And then parallel to the xy plane, that's where z equals a constant, we get x squared plus y squared equals a constant. Those are circles. Anybody, before we start drawing, know what this surface is going to be?
No.
The sides are lines. We're going to connect those lines with circles. This is a cone. All right, so in the xz plane, we get lines. So we get a line going up this way, and we get a line going down below as well. And we get a line going this way, and a line going down below. In the yz plane, we also get a line. I'm not going to draw the other line, but these lines are connected by circles. And there's a circle down here. So we get what we call a double naped cone, because we get a cone above and below. And I can make the top of my cone like so. But it keeps extending on infinitely. So this is a double naped cone. Yeah. No. So we're talking just about the surface, just about the outside part. So we could define if we wanted to define a solid cone, we would have to say for the region where x squared plus y squared is less than that constant. Or you just say the surface and its interior. But we're just talking about the outside. For all of these, we're just talking about the outside part.
More effective since this would just be a one. That's the same line, just spun around.
Yeah. So we will talk about a lot of these surfaces we can visualize as quadratic surfaces or surfaces of revolution. And we'll talk about coming up with equations for surfaces of revolution on Thursday. Because we can think of a cone as the surface generated by revolving a line about the z-axis.
Couldn't you also revolve on any axis? That would also be.
Yeah, we'd give us, this particular cone would be revolved around the z-axis. Now the equation that we would get here would be different depending on which axis we revolve it around. All right, so there's our introduction to our 4 basic surfaces. We will become, over the next 5-6 months, we will become very familiar with these surfaces. Until May, right?
So we should probably get into drawing.
Yes, we will do a lot of drawing. And what will happen is eventually you'll just be able to look at the equation and say, oh, that's a paraboloid. And you'll be able to draw a sketch.
The drawing is going to be more challenging than the identifying. I try to make it actually look like the pictures.
So the first problems are about spheres. And the second set of problems are about cylindrical and quadratic surfaces.